This video is going to cover some uniform circular motion, I'm sure, somewhere in there, but mainly Newton's law of gravity and orbits of planets and satellites, which would be Kepler's laws. Oh, and right there. So Newton's universal law of gravitation says that there's a force of attraction between every two objects, which is proportional to their masses and inversely proportional to the square of the distance between them. This is that 1 over r squared relationship. So it's g m1 m2 over r squared, and the g value is on your formula sheet, but it's right there as well. Which means that the force of 1 on 2 is equal to the force of 2 on 1, according to Newton's third law, equal and opposite forces. These are going to be equal and opposite forces here, whereas this vector is indicating direction. They are equal in magnitude and opposite direction. Planet has 2 moons of equal mass. Moon 1 is a circular orbit of radius r. Moon 2 is in a circular orbit of radius 2r. What's the magnitude of the gravitational force exerted by the planet on Moon 2? It's going to be 1/4 as large as that, because that 1 over r squared relationship. On the surface of the Earth, little g should just be mass of 1m times the mass of the Earth times the radius of the Earth squared, or actually it's the radius of the Earth plus the height above the Earth squared. Because the radius of the Earth is so large, though, if we're within a small height, we can just kind of call this 0. And so that's where we get the 9.81 value for radius of the Earth, because this force, gm1 m2 over r squared, was equal to mg, and so that m canceled out. And so here it kind of gives you some of the values. 9.8 at 0 kilometers above the Earth. Get to 1,000 kilometers, it starts going down. The gravitational field is that G particle. We haven't used that a whole lot in mechanics, but it's similar to like an electric field, where the electric field was the force of electricity divided by the charge. Well, now the gravitational field is the force of gravity divided by the mass. And the gravitational field will always point towards the Earth. All right, Kepler's laws. Kepler is a guy who studied astronomy for quite a while. He helped with Brahe. And then he came up with 3 statements to describe planetary motion, and they're still just as true now. All planets move in elliptical orbits with the sun at one focus. The radius vector drawn from the sun to a planet sweeps out equal areas in equal time intervals. And the square of the orbital period of any planet is proportional to the cube of the semi-major axis of the elliptical orbit. Okay, this one here, all planets move in elliptical orbit with the sun at one focus. That means as the planet gets closer to the sun, it will speed up, basically because the force of gravity has decreased between the sun and that planet because that r squared term has gone down. So as the potential energy and the force of gravity between two objects decreases. Oh, I'm sorry. Let me say that again. As an object gets closer to the sun, as a planet gets closer to the sun, it will speed up. And then as it's on the part of its elliptical orbit that's farther from the sun, it will be moving at a slower speed. So it speeds up as it's close by and slows down as it's farther away. Let's see if they've got a picture of this. Here we go. Kepler's first law. An object would, if this is the sun right here, it would speed up, slow down, speed up, slow down, speed up, slow down, speed up, slow down. And that's based on conservation of mechanical energy. Or you could say that the force applied by gravity is going to result in the change of kinetic energy of that planet. All right, the second law says that this area is traced out during that time period. Well, the second law is very similar to that because it speeds up and slows down. The area from here to here is equal to the area from here to here in equal times an equal area is traced. And
I
then
just want to tell you one thing. Can I do a fashion show for you?
All right, and then the third law is based on this is, let's see if I can come here. So we know that the speed of an object is v squared. 2 pi r over the period would be the speed of an object. And we've done that because 2 pi r is the circumference, that's the distance traveled, and t, this big T, is the time for one revolution. So if you say v is equal to 2 pi r over t, and you say that the acceleration of gravity, the centripetal acceleration of this object is equal to g times mass of the sun divided by the radius squared, then you could say this centripetal acceleration is equal to this centripetal acceleration, where this is v squared over r. If you square that term and rearrange it, you get that the period squared is proportional to the radius cubed. And this is all constant because 4, pi, g, and the mass of the sun are all constants there. And so that's where you're getting this ks. But every time I work that out, I have to basically say that the acceleration of gravity, g times the mass of the sun over radius squared, is equal to v squared over r, and then I have to kind of figure out that this is 2 pi r over a period. But here it is. I don't think that's on your formula sheet. And this a is distance from the sun. And gravitational potential energy, again, is negative F dx. We've seen that any type of change of potential energy is equal to the negative F dx. We've seen that already, which means it's negative GMM over R, because that other R was the squared part. Potential energy goes to 0 as it approaches infinity. It's large it's very negative here, and then goes to 0. It's kind of because it's got that negative sign. It's not exponential because but it's an inverse function on the bottom there. All right, energy considerations. That's what I was just talking about. The total energy of a planet or a satellite or something like that is going to be its gravitational potential energy plus its kinetic energy. And so as it gets closer, for circular orbits, total energy is negative GMM over 2R, so assuming there's no change in gravitational potential energy. For elliptical orbits, it's over 2A, where A is the major axis. These are going to be more conservation mechanical energy problems, though. A comet moves an elliptical orbit around the sun. Which point in its orbit represents the highest value? I'd have to look at which one's which. I always get those mixed up. I think this one's when it's closest and this one's when it's farthest. The speed, I could actually do it by this. The speed of the comet will be greatest when it's closest, which will be, which one's closest? Yeah, okay, so that one's right. The potential energy will be greatest when it's at its aphelion. Kinetic energy will be greatest when it's got greatest speed, so that'll be at its perihelion. Total energy will be the same all the way through. But notice it said of the comet's sun system, it did not say of just the comet. But it just said the comet, the total energy would be greatest when it had the greatest kinetic energy, because you cannot include potential energy unless you've got the two parts of that object. And satellites. The escape speeds, the speed it would have to break the surface of the Earth. It's 2g over m, or 2g squared root of 2gm over r. I'm not going to worry too much about that. I don't think you'll see it. So if you want to kind of look at it now. We're not going to go through black holes, but black holes, nothing can get out of it. I'm not going to talk about dark matter. Okay, so we've defined gravitational field there. There's Newton's universal law of gravitation. Kepler's laws, this is the gravitational force. Kepler's laws, again, that's his third law. And we went through the derivation of that. Gravitational potential energy is, the change of gravitational potential energy is negative integral of f dx, which is where we get this. And for circular orbits, it's always the same speed at every point. And there's the escape speed. Yep. And that's about it for this one. Got one more on oscillations.